now. So if you want to
Yeah, okay, that's fine.
make the introduction.
Hello and welcome to our webinar. I'm Pete Starkey, a member of the Council of the Institute of Circuit Technology, which is dedicated to technical aspects of printed circuit board manufacture and assembly. The Institute continues to successfully provide its members with opportunities to improve their knowledge of manufacturing process technologies, materials and practices, and to stay in touch with current and future developments. The future of printed circuit manufacturing and assembly will rely heavily on automation and the establishment of the smart factory. What will this involve and what additional skills will engineers need to learn? A leading expert in this area is Happy Holden, Honorary Fellow of the ICT, who was kindly offered to deliver a series of 8 one-hour webinars based on his recently published ebook, 24 Essential Skills for Engineers, which is free to download from the iConnect 007 website, and which will form a valuable resource for in-house training of engineers and their career development. In his initial presentation, Automation and the Journey to Your Smart Factory, Happy introduced the elements of the journey and discussed the key issues: who, what, how long, when, and how much. His emphasis was very much on avoiding factory automation consultants who will generally charge you for learning your processes and procedures while selling their own equipment and software. Indeed, Happy suggested that you select your own engineers who are familiar with your own processes and procedures and let them learn how to do the automation planning. Then they can teach others this essential skill, which the factory will need over and over again. Last week, he discussed total quality control, Six Sigma and statistical tools, problem solving, design of experiments, and predictive analysis. In today's presentation, the third in the series, Happy focuses on the following skills: benchmarking, product and process life cycles, engineering economics, and road mapping. If you have any specific questions, please direct them to happy@iconnect007.com. So it gives me great pleasure to hand over to Happy Holden. Happy.
Well, thank you, Pete. As always, we're thankful for the ICT for helping to put together this program. It comes at a really important time in our industry, with the entire world looking at reevaluating their supply chain, and also the enormous investment being made in semiconductor production, which of course is going to require printed circuit board and packaging in order to be implemented. So the next 2 to 5 years, there's an enormous opportunity for everyone, if you've tuned up your business plans, to find the financing available to expand your business. Now, we have people from all over the world attending this webinar, so good morning to some of you, good afternoon, and good evening, depending on where you're coming from. We can't predict the business that you're in or your business plans, and so we're focusing on what I believe are 14 of the essential tools and skills required in putting together this automation part. We're particularly focusing on automation and the smart factory, hardware and software specifically. But, the skills and everything else apply equally as well to if you're developing new technology or new process. So with that, we'll get started with the with that. The skills today are additional for benchmarking, product or process life cycle, engineering economics, about the return on investment, break-even time, and road mapping. These are all essential tools and skills that go into doing your business planning, especially the automation or the focus on the smart factory. And like as Pete introduced, the last two have been the introduction and 3 other skills. The next 3 lectures after this will be more on the automation methodology, the smart factory, and sensors and chemical analysis. And then after that, the latter 2 will be, again, skills and tools to put together the program. A lot of this comes from this 24 Essential Skills. Hopefully you downloaded this because I'm spending 15 to 20 minutes on essentially each chapter that provides more information if you read the chapter and look at the references. Again, as I mentioned before, spending 15 or 20 minutes on classes that I took over my 50-year career that were a day or 2, or even some of the courses were 5 days. Certainly all I can do is introduce how important this is. And then on the very last lecture, we'll talk about distance learning, which is typically the technique you'll use individually to enhance your understanding and skills. Distance learning wasn't available when I first took these face-to-face. In fact, interesting enough, distance learning was developed by my brother, my younger brother, for the U.S. Department of Defense, and was a focus of his PhD in sociology, that is the theory of learning theory, to develop courses for our armed services, sailors, soldiers, airmen all over the world. As many as 60 to 80% of those serving in the U.S. Armed Forces were involved in distance learning techniques to improve their skills. So this is a highly refined area that we'll cover on the last lecture. The first one, benchmarking, is really important. It's a process that measures how a company is performing against industry leaders. It's used to better understand how companies perform, but it also helps your company develop plans to improve or adapt specific practices. A benchmark is used to measure performance using a specific indicators or metrics, resulting in a metric of performance that is then compared to others. A subset of benchmarking is the activity of teardown. At Hewlett Packard, this is a very, very serious activity that I participated in during my 30 years at Hewlett Packard. All product lines conducted benchmarking on competitors' products. For instance, this was a lot easier than for a complex computer system, but in all cases, the detailed process was the same. We would document all benchmarking activities by narrated video, high-resolution cameras, X-rays, and microscopes. Benchmarking advertised performance using industry standards and discover the maximum minimum performance metrics. Benchmarking physical parameters, size, energy usage, heat produced, etc. We would benchmark electrical parameters, power supplies, number of PCB, special electrical devices, etc. We would benchmark the product disassembly and actually calculate its DFMA metrics in terms of how simple was it to assemble and estimate the cost and productivity in assembly. We would then benchmark each PCB assemble in terms of solder type, conformal coating, heat sink, number of parts, different part types, and benchmarking each printed circuit board, which my organization did in terms of size, layer, design rules, wiring efficiency, special features, materials, distributed capacitance, sensing. And we would even benchmark custom integrated circuits on each printed circuit board, including the silicon type, number of gates, and design rules using fuming nitric acid many times. And it's quite a job to count the number of gates and design rules of an integrated circuit. And then all of these information was collected with the metric photos and videos into a multi-volume report. Now, some people may call this reverse engineering, but for Hewlett Packard, what we were looking for was, number one, did our competitors' products perform as they advertised? And number two, did they utilize technology that we weren't aware of or that were superior to our technology? If we would discover such a thing, that then formed, like we're talking about here, goals and improvements of our own roadmap in terms of our products and capability. But it allowed us a deep understanding of technology and how everything works together. A lot of this is done. Many universities and a few companies do this for profit. One of the best known is Portelligence, headed up by David Carey, that I worked with at Sematech. The Austin, Texas company produces teardown reports and related industry research on wireless, mobile, and personal electronics. Here's the original big Motorola analog cellular phone that started the whole mobile phone business kind of thing. Now, like I said, from a teardown like this, we would actually produce a book that got all the way down to cost and materials, design rules, and other factors. A little more interesting is this teardown of a computerized 3D tomography. In other words, if you're at my age, you're used to colonoscopies. Well, this is the technology that's going to replace colonoscopy. It's this little pill that you swallow, and then the doctor navigates this through your GI tract with a camera and other techniques. They're now proposing that this pill will have little manipulators in case they discover a polyp or something like that. It'll actually take care of it. So miniaturization is one of the metrics that we focus on, and this is certainly a terrific example of it's interesting. There's a deposit you pay on this pill. It's behooves to return it, after the examination. The key reasons for benchmarking and contrasting approach is not necessarily reverse engineering, but it helps defining customer requirements. Rather than using gut feel, you have market reality and objective evaluation to help establish goals and objectives, that are credible, arguable, and provide proactive measurement. But this also develops measures of productivity to help solve problems and understanding the strengths and weaknesses and defining what is best industry practices compared to where you are today. This is a route to become more competitive with a concrete understanding of competition, new ideas of proven practices and technology, and a high commitment. Proactively search for changes, many options in business practice for superior performance. It's interesting that if people did this more and they were benchmarking or disassembling some key Hewlett-Packard products, they would have discovered that Hewlett-Packard doesn't have power layers anymore. Starting in about 1996, we developed a technique similar to IC design, in which we eliminated the power planes and replaced them with a power mesh with up to 12 different voltage rails. This was not only higher density, lower cost, but achieved much higher frequency performance than an entire plane. But people never wrote about that or even discovered it because they failed to dissect Hewlett-Packard multilayers to realize that we were doing something totally different, because we did not patent the technology. We kept it a company secret, which means if you're dealing with secrets and things like that, the benchmark is one of the few ways to find out, well, what else is somebody doing that may be a better idea. So the technique of doing this is one of setting up your team, identifying the companies for comparison and or the products or the technologies that you want to determine how data is going to be collected, the methods in collecting that data, determining current performance gap between your own performance and that of what you're measuring, and then looking for future performance levels, and then communicating the benchmark findings and getting established, and then using this to establish functional goals and developing action plans, on and on. The conceptual one is that if we have this industry best practices, and you're looking at functions being measured, where do you stand with respect to the best in the industry and measuring this benchmarking gap? And then over time, setting up your roadmap and program such that you are the superior performance compared to industry's best practices. Like I said, if competitors aren't doing benchmarking, then they may not know aware of that you're superior or taking that in profit margin or market share gain. So there's a thing called the Z chart we developed, looking at the historic performance of improvements to lessen our competitors and focusing on benchmarking gaps and the need for strategic action, and then continuous improvement for the future. Example of this may be here in Excel that I've taken from some examples on the internet. You can use, simple Excel things, absenteeism rate, time to process customer order, mobility enhancer consumptions or spoilage, or any of these other business goals or business measures of performance. One in particular, here's a benchmarking of HP printers, HP. We're talking here about the first of the inkjet printers called the ThinkJet, which was black and white over there in the bottom right. Then we went to the QuietJet, which was black and white, and then the DeskJet, which was color. The first two were fan folded paper, the third was cut sheet. You can see some of the measures of performance that we get on design for assembly in terms of number of parts, ease of assembly, and assembly time. And this was compared to Oki 182 black and white fan fold printer and an IBM Pro printer black and white, again with fan fold. Fan fold paper simplifies paper handling much more than cut sheet, but you can see that the early DeskJet prototypes using these metrics was redesigned looking at our competitors in terms of having a lower assembly time or ease of assembly that was better than our competitors. Now, I had the fortunate of being the CTO of Foxconn in China, and we built the HP inkjet printers for Hewlett Packard, but we also built Japanese and other American and European printers. And I can tell you, actually seeing the reports on quality, repair, rework, that the Hewlett Packards were constantly superior to any of the other Japanese, European, or American products, such that these numbers right here from that looks at the design of the product, years later when I'm actually building them and have comparison data, the HP products were constantly more robust and easier to assemble and higher quality than competitors that we build at Foxconn. So another thing is product and process lifecycle. I bring that up because if you develop a benchmarking capability and you're a fabricator or assembler, then you can offer this service to your customers, that are taking your activities and services and going into their final product. By then, you can contribute your expertise to where they are in terms of their competitiveness, and help them develop their roadmap. But you also may choose to focus on technology and be focused on developing a new process. And so there's a life cycle in developing and implementing a new process in your manufacturing. So the product life cycle is fundamental to a corporation's intent on developing new products or processes, sometimes called the new product introduction. Specifically, we actually have a free ebook specifically focused on new product introduction, NPI, if you're interested. And this product supports enhancements and eventually the obsolescence. I was introduced to this PLC process very early in my career because my first large PLC was the HP 35 handheld calculator in 1971. And I would practice the PLC on this and succinct calculators for the next 20 years that I was in Hewlett Packard. But that first HP 35 was quite revolutionary in its. So the PLC process consists of developing, prototyping, manufacturing, and supporting and even obsoleting a product or process of an organization. And it's one of the most important of procedures that was used at HP. HP derived their high profit and stellar reputation because of the innovation in their measurement instruments. HP prided itself on being able to measure anything physical. Later in the 70s and 80s, as they expanded their product line, this included chemical, medical, nuclear, and genetics in the 1990s. And as the company grew and diversified, so did the number of products, reaching a peak in 1985 of 27,000 separate products having 35,000 electronic options. Because of the state-of-the-art nature of most of these products, their life was only about 3 years before a better version was created. Many of the first generation came from HP Laboratories and their investment in groundbreaking concepts, but the majority of new products came from customer feedback and their needs. So product development follows what we call the S-shaped curve over time. The phase review process for either a product or a process, starts with the vision and the Rev A and moves through the evolution of that. As a system phase review, starting from phase 0, which is requirements of the plan, through phase 1, studying and defining it, specifying and designing it, developing it, testing it, users test, ramp up, enhance and support, and then maturity. The phase review process is a very, very long document if you choose to learn more about these. And it includes a lot of management things. This is a product definition flow chart of phase 0, phase 1, and phase 2 from the manufacturing pool, new technology pool, management team, product definition efforts, quality functional deployment, which we'll cover later, and benchmarking and competitive information. This was what I use in terms of the actual process phase thing, because these are checkpoints and milestones in which, as we develop and then come to conclusions, we focus on have we achieved and not forgotten something in the team as we move through the phase of enhancement, or should we can it and kill it because we're not some of our activities or assumptions were incorrect and not supported. This is supported by what we talked about TQC before, and the use of the 7 product definition phases that we talked about in the last lecture. The product definition process, follow processes, the process self-tests, and the process action part. So the changes in the payoff and product lifespan over the 2000s, electronics has the shortest product lifespan that has fallen 46%, and the shortest break-even time, 5.5%. This has the effect of squeezing the time the product should make profits. And so if you look at car components, car assembly, general engineering, process plants, electronics has the shortest product development lifespan, which is decreasing all the time, which emphasize that you really need a process and procedure how to accomplish this, or get tied up or fall behind. Because the interesting thing is about the profits are made very early on with a new process or a new product. Once the product is out there, people can benchmark it, disassemble it, and again, copy it or change their designs. And so as sales ramps up, the profit improvements. And so that we developed what we call the break-even time. And the break-even time will be discussed in engineering economics, which is a little bit different than return on investment section. The benefits of early introduction of a product to a market, provides a larger market share and a longer, profitable one before competition may derive and focus on price reduction of products. And this is a whole chart of the typical process using QFD. Quality functional deployment is a systematic planning process. We'll cover that in the latter lectures. This one is one of the most complex. Like I said, I had a 5-day class on this one. This technique was developed by the Japanese and highly refined by Ford Motor Company. But we'll talk about that later. Engineering economics is an interesting one because it's fundamental to engineering that, especially for manufacturing support, what I'm focused on here is that for a process engineer in printed circuit equipment and automation of production or assembly, the class that I had used the principles of engineering economics written by the Stanford University professor Grant Ireson. Interesting enough, the book was also the basis of our 1973 financial calculator from HP, which had some controversy because it was focused on engineering economics and not the typical university focus of economics. The primary variables that make up all interest formulas is interest rate per period, number of interest periods, present sum of money, future sum of money for end periods, and end of payment. These calculations lend themselves to spreadsheets and are found as part of Microsoft's Excel as well as calculators. So they have abbreviated ones. The single payment compound amount factor is called CAF prime. The single payment present worth factor, PWF prime. Series sinking fund factor for a series payment, SFF. Series compound recovery factor for that series. Series compound amount factor for future value, and series present worth factors. So when we talk about return on investment or the business payback of an automation proposal, technology proposal, or product line diversification and worker improvement in productivity, one of the things that everybody looks at is return on investment, which is the equivalent bank interest rate of all the money you spent and all the profits you made over a fixed time frame. A second measure is net present value, which is the current value of all the cash flows over time, assuming cash is worth X percent, say C percent. A new one you may not have heard of is the break-even time, and this is the time to money, which is the time looking at profits that it takes to pay for all that you have invested in order to gain those products, or how long before you truly make a net profit in that. Time value of money is the overall discussion of these topics. Because of inflation, future money is worth less than current money, or it's discounted. And this includes things like depreciation that is set up by the government that allows you to deduct each year as it gets older. Like I say, the common practice in equipment justification is to calculate ROI, or the net present value. But you got to ensure and include all of the aspects of cost and savings involved. And the rate of return is easily calculated by Excel. To do it manually requires a trial and error calculation of assuming an interest rate, which Excel will show you how to do. Just as an example, showing the interaction of all of these, I have an investment of $1,000 over a period of 10 years and an annual interest rate of 6%, and using the future value of that over 6% in 10 years is $1,791. But if we were to look at only 6 years, it would be $1,263. And then you can see that taking these different cash flows and using different times, these factors allow you to get period payments or equal flows, or savings would be, or will be started. So it's relatively easy for an engineer to study and learn this, but very useful. This is one of the first automated equipment justifications I did when I first entered Hewlett-Packard in 1970. And the Hewlett-Packard that I entered was all manual production in printed circuit and assembly. And so, putting together my engineering economics and understanding of automation, we put together this first proposal in terms of investment of $415,000 over 8 years in terms of calculating the return on investment. This was a copper tin lead pattern plating line with a rack strip, and purchased in 1991 with an 8-year operating life and a 5-year depreciable, with capability of 500 18 by 24-inch panels per shift. The load was 2 rows of 4 panels each, and then there's the process that looked like. And like I said, this was used because there were 5 or 6 different methods of automating electroless copper and or electroplating copper, tin, gold, versus how many additional laborers we would have to hire in order to get a particular two-shift output. This is one of my first ever papers presented in NEPCON Anaheim in May of 1972. But the return on investment clearly indicated that rather than hiring 15 to 18, 20 more electroplaters, it was time to invest in one of these different types of sidearm or split rail or triple hoist, dual hoist, or quad hoist into that. A little later, I learned about break-even time. The example of break-even time. Break-even time was developed specifically when, because of changes in assumptions or other factors, we were not going to necessarily meet the introduction date of a new product or a new process. But this helped, show to management that what was going to be happen to our break-even time under the current conditions. But if we added more resources, more people, or more money, or some alternative right now, how this could help us recover the break-even time or actually improve the break-even time in terms of accumulated discounted dollars. So break-even time as a performance monitor uses the TQC tools to monitor product development performance using aggregated break-even time. Understands the company's competitiveness is increasing, and the use of TQC tools to monitor product and process performance using aggregated break-even time. And so, reading this chapter is particularly useful on the financial and cost of a particular automation or smart factory project. But there are many metrics used for new product development or new process. What if scenarios, project selection, in-process control, should more resources be applied to the project, process improvement, and provide insight into future projects. But the break-even time is not a panacea. Some of the limitations considered when applying include to need to balance break-even time with other factors that are not strictly financial. Break-even time is not comparable across businesses. It varies greatly business to business. And break-even time can predict and measure investment and profits for complex business. It became very difficult to determine the associated break-even time used in many complex products. Other engineering spreadsheets that you could develop, that I have developed: major equipment versus old equipment or manual labor, yield improvement using new materials, process machines, process changes to improving the process using new materials or machines, technology acquisition using new material changes justifying the changing of materials, environmental improvement, safety improvements, the customer required changes, and labor shortages and staffing issues. Which brings us to the last one, which is road mapping. A lot of this activity goes into creating the roadmap, and a technology roadmap is a plan that matches short-term and long-term goals with specific technological solutions to help meet those goals. It's a plan that applies to a new product or process and to an emerging technology. And it helps reach consensus about a set of needs and the technology required to satisfy those needs. It provides a mechanism to help forecast technology development, and it provides a framework to help plan and coordinate technology development. So road mapping contributes to more intensive competition, shorter time to market and product life cycle, reducing higher costs and the risk of research and development, or increasing government regulations or greater environmental sensitivity. So industry today, the vision, the industry goals, the technology roadmap is one way of realizing those visions and industry growth through R&D or technology deployment or partnerships for the industry of the future. Historically, a roadmap has been organized by our IPC. IPC doesn't do that anymore, but Sematech and SIA and NEMI and OEMs still provide roadmap. The government has a roadmap. In fact, that's very interesting, the roadmap the government has put together at NIST for the 52 billion US dollars they're going to invest in semiconductor and association and technologies and manpower. But a lot of this goes into the National Technology Roadmap for Electronic Interconnection. And from these roadmaps, OEMs provide plans, committees, focus on projects, and university and national laboratories focus on basic R&D or applied R&D, and companies then can utilize that. So, the road mapping at the broadest sense supports the industry and consensus required to satisfy the needs. It provides a mechanism for helping experts forecast technology developments in targeted areas. It provides a framework supporting the planning and coordination of technology developments within a company and or an entire industry. It helps identify critical technologies and or technology gaps, creating barriers to product formation targets. And it identifies ways to leverage R&D investments through coordinated research activities, either within a single company or among member companies. So the type of the quality of information and the type of roadmap, early on could be, facts as perceived by stakeholders, which is eye-opening for many. It's the first look at the business time content. A zero-order roadmap is a serious attempt at consistent vision, evolving to a first-order roadmap, which is first full roadmap, but with limited backup for forecast of people and process needs, and then a second-order roadmap, which is the full roadmap and its robustness. So I have here a number of examples of roadmaps, and this one is for nanotechnology, in terms of from 100 nanometers down to 1 nanometer and the atomic molecular level. Interesting enough, the SIA roadmap for semiconductors now talks about angstroms. So we've passed the nanometer level of the roadmap in the semiconductor, and the semiconductors roadmaps now talk about angstroms. And within your lifespan, you will see from angstroms to atoms in terms of semiconductor geometries, as well as other nanotechnology, because it's not just semiconductor in computer and it's medical and health and networking communication in terms of 5G, 6G, 7G, food and agriculture, energy and environment. So roadmap process is really kind of 5 steps. The current state, end state definition, the formation of the plan, initiative definitions and technical assessments of organizational, functional, and then prioritizing and fit those assessments together, and then provide a roadmap and planning the product. So the roadmap process in 5 stages, again, was the preliminary activity phase output from current work, roadmap development phase and then follow-up activity phases in terms of expert bias. You know, we don't know what we don't know. Roadmap to the product into the 5 stages of that, and then assessment of what each of those stages are within that. So there's an example of a roadmap from Texas Instruments digital signal processor, which they're particularly famous for, you know, over time in terms of infrastructure video, client video, and portable video, their roadmap. This one is master data management roadmap, which is quite interesting and informational in terms of putting together the roadmap. This one is even more introductory, you know, in terms of, you know, quite a project roadmap of many sorts. And this finally this one of a, you know, a roadmap from an industry in terms of initiation, project setup, execution, transition, in terms of the strategy, design, transition, operation, and then CSI. So with that, I hope that this provides you some help, you know, in looking at these 4 tools or technologies or techniques and skills that you'll spend time, if that's useful in whatever your business plan or implementation for automation will be. Starting next week, we'll start to talk about the networking and computerization for the smart factory and the automation. And you'll be interested to know that this has been going on for a long, long time, but mainly, you know, in the bigger OEMs like General Motors or General Electric, you know, the big guys, which I was involved with in the 70s, 80s, and 90s. But now the costs have declined and the software and other solutions have increased significantly. So it's now down into the price level that we can afford and deal with. So now is the time to start looking at your fundamental business plan, where you want to go the next 2 to 5 years. And with that, thank you for your time, and I hope to see you next week. And if you think other people should be involved, don't hesitate to give them a call or ask them to contact Bill and sign up for this. With that, thank you for your time today.